thank you very much for being willing to give us this talk tonight. You are quite literally a master of your art. I think Tim must be one of the most regular contributors, amateur pro-am cooperation with these regular contributions to the AAVSO. You can also look at the article in today's Manasseh or the weekend's Manasseh, as well as Magda Stryker's contribution to the same. Tim has been contributing towards science for many, many years, ever since I can remember. And I think he was duly rewarded when he, if you look at his brief resume, he was awarded, I think, the 3rd Overbeek Medal, or it might be the 4th, together with Magda in 2018. So he is really an observer and a scientific reporter of note, and we're very privileged to have you as our guest speaker tonight, Tim. We're looking forward to hearing what you want to share with us.
Thanks. Go ahead, Tim.
Thank you. Thanks very much. Can I share my screen?
Yeah, go ahead, Shane.
Please let me know when you can see it.
Okay, that's it. It's up now. You can go ahead.
Okay, so it seems we've got some connectivity issues tonight. We've just come out of 4.5 hours of load shedding. We had power for about 3 minutes and the power's gone again. So I'm sitting here pretty much in the dark. So let's just hope this is going to work. So thank you very much for inviting me to give a talk tonight on meteors. So if you look up on any clear night, you're bound to see a handful of shooting stars. Of course, we know that these are not shooting stars at all. They are, in fact, small dust particles, and they are the debris that is left over from the formation of the solar system. So this is a meteor here. If you know your stars, you can see the constellation of Orion is here. And this particular meteor is coming from the direction of Gemini. So this is a Geminid, and there are 1 or 2 other fainter ones on here as well. So these are meteors. Often we get confusion with the word meteor and meteorite. So first of all, let's just start with maybe a few definitions. And these were definitions were approved at the IAU Commission in April 2017. And so it was agreed that a meteoroid is the term we give to a solid natural object of a small size between 30 microns and about 1 meters, moving in or coming from interplanetary space. A meteor is the light and associated physical phenomenon which results from the high-speed entry of a solid object from meteoroid into the atmosphere. So a meteor is not the actual particle that you see, it's the effects of the particle coming into the atmosphere which results in a meteor. A meteorite is any natural solid object then that survives that and reaches the ground. So if you find an object on the ground after you've seen its passage, it's a meteorite. If you don't find an object, then it's classed as a meteor. A meteoroid stream is a group of meteoroids which have similar orbits and a common origin. A meteor shower is a group of meteors produced by meteoroids of the same meteoroid stream. And then we classify any meteor which is equal or brighter than visual magnitude -4, so about Venus brightness, as a fireball. And if the fireball is seen to explode, it's called a bolide. And then any very bright bolide which is seen to explode, absolute visual magnitude -17 or above, is called a super bolide. And bearing in mind that the full moon is around about magnitude -12, between -12 and 13. I've lost my screen. Do you still see it?
Yeah, we can still see your screen. You still got the definitions slide up.
Okay, still okay there?
Yeah, okay, we see the
My
pillars of creation.
my computer's doing funny things. Okay, so so the meteoroids that you see then, these are the debris left over from the formation of the solar system. So they have their origins in these giant molecular clouds. You're probably familiar with these pictures. The left-hand side one from the Hubble Space Telescope, right-hand side one from the James Webb Space Telescope. These are known as the pillars of creation, and they're areas of starbirth in the giant molecular cloud of the nebula, which we refer to as the Eagle Nebula M16 in Serpent. So if you look more closely into these, and this is a close-up of the James Webb Space Telescope image, you can see the process of star formation taking place. So these small red dots that you see here, these are all new stars which are being born out of this gas and dust. And this composition of this material is around about, or mainly 99% hydrogen and helium, which is remnants of the formation of the Big Bang. And then there's around about 1% there of dust and heavier elements which are formed in supernova explosions, and they are then ejected back into the interstellar medium. So once these giant molecular clouds start to collapse, they form what we call these protoplanetary disks around the host star. These are, again, Hubble Space Telescope images of a number of protoplanetary disks, or Aquariids for short. And these are new stars, and they have infant solar systems forming around them. So out of these solar systems, there will be planets formed, and then left over once those planets are formed will be these dust disks. And these dust disks then is the remnant dust which is left over from the formation of these solar systems, and this is what we see as meteoroids when they come into our atmosphere. So this is the remnant dust disk from the star Beta Victoris. It's quite an old picture, taken before we had even the Hubble Space Telescope. But now with modern telescopes, this is a Gemini image from the Gemini South Telescope in Chile. And these are remnant dust disks around stars. And all of these basically then are areas where on the outskirts of the solar systems of these stars, there are comets formed. So we know, of course, then that our own solar system is surrounded by two sources of comets. We have, on the one hand, postulated in 1950 by Jan Oort, the Oort cloud, and it's a spherical ball of material which surrounds our solar system, the remnant of the solar system. And then 3 years later, Gerard Kuiper postulated that there must be a remnant disk of material left over, the dust, which was left over from the formation of the solar system itself, and this we refer to now as the Kuiper belt. And that's what you see here. And then in the center here of the solar system up to the major planets, Uranus, Neptune, and then outside of that, you have the dust which is left over from the formation. And this is the material then that's incorporated in comets, and comets are the primary source of most of the meteors that we see in the night sky. Okay, so we know pretty much where the dust comes from. We know that it comes from comets. At the time that Edmund Halley was doing his pioneering work on cometary orbits, it was suspected that meteors were in fact exhalations or material which is coming from the interior of the Earth and being expelled, and meteors were thought to be nothing more than the ignition of sulfurous vapors being exhumed from the Earth. So Edmund Halley then he observed a bright bolide on the 19th of March 1719. He collected observations from a number of observers around the west of England, and as a result of that, he was able to triangulate the bolide, and he came to the conclusion that it evinced him that the altitude of this object had to be more than 60 English miles above the surface. So 60 English miles is very close. In fact, he came to a value of around about 63 English miles, which is about 103 kilometers. And that is almost exactly the altitude. So that was in 1719. In 1798, Ernst Chladni, he was a German physicist, he showed that meteors could not be explained from the accumulations in the upper regions of the atmosphere, and he postulated that they must be coming from outside of our atmosphere. It wasn't until the outburst of the Leonids first of all in 1799, but then specifically in 1833, and the return of Comet Tempel-Tuttle, which has a 33-year orbit. It was realized that the Leonids, which are related to that comet, were also returning every 33 years, and that proved the first link that proved that meteors had comets as a source. So this is a woodcut from Adolf Folmy. He did this woodcut in 1833. This was the picture of meteors raining down in North America on the night of November, I think it was the 17th of that year. And the rate at which these meteors were coming down was around about 50,000, or estimated between 50,000 and 150,000 meteors per hour. To put that into context, if you divide that by whatever it is in seconds, that equates to around about 14 to 42 meteors per second coming from that comet. So we had the first proof then that meteors have comets as a parent. So with that in mind, it's useful to understand a little bit about comets and how they produce the dust particles. So comets then are the reservoirs of these dust particles which are left over from the formation of the solar system. This is a picture of Comet Halley, which was very bright. It reached 0 magnitude in 1997. It's not the parent body of a meteor shower, but it's useful to have a look at this picture because gives you a good idea of what comets are made up of. So on the one hand, you see the nucleus is over here. It's surrounded by a bright coma. Streaming away from that coma, you have then the ion tail or gas tail, which is this tail here, and that is shining blue in the light of ionized carbon monoxide. And then you have here this long dust tail. So this white tail here is the dust tail, and that is reflecting sunlight. So this comet was studied in some detail. We know that comets then, if you listen to Fred Whipple, that comets can be likened to a dusty snowball. So you have these frozen ices, and embedded in these ices, you have these dust particles. So these ices have been analyzed in some detail. In the case of Hale-Bopp, the abundance then, the three most abundant volatiles are water, carbon monoxide, and carbon dioxide. And then when these materials when the comet is far from the sun, these are frozen. As it gets closer to the sun, these materials, they vaporize, they form a vapor. And this is the composition of the volatile vapor that was discovered in Hale-Bopp. So for most comets then, the predominant volatile is water vapor, and then smaller amounts of carbon monoxide, which is the primary driver of the comet's brightness when it's far from the sun, and then a smaller amount of carbon dioxide. And then we also have then oxygen compounds, sulfur compounds, nitrogen compounds, and small amounts of hydrocarbons. So that's the general composition. If you look at the composition in more detail, this is the inventory of all the volatiles found in Comet Hale-Bopp. Again, you can see here water vapor, carbon monoxide, and carbon dioxide. These are the three most prevalent, but then various amounts of these others. And these are different molecules, vary from comet to comet, and their abundance in each comet varies from comet to comet. So there are a few exotic things here, apart from carbon monoxide, carbon dioxide, and water. Somewhere here we have hydrogen sulfide. So the comets are quite smelly. smelly environments to be in, if you could smell them. They're also very toxic. So you have here hydrogen cyanide. And then you have other molecules, for example, like formaldehyde, which can be polymerized. That's polymerized on Earth to give you a plastic, which we call acetyl. And that simple polymer of formaldehyde has been found in comets. So there is even plastic in comets. There are some also some more exotic molecules. For example, here there's glycine, amino acetic acid, glycine, and that, of course, is one of the building blocks for life as we have it on Earth. So much for the volatile compounds. Then there's also, as I said, there's a dust component of comets. This, for example, is typically what a cometary particle might look like. This was a particle which was collected in 1982 from a high altitude aircraft which flew at an altitude of 20 kilometers above the Earth's surface. It deployed a paddle with a sticky surface and collected these particles and brought them back. And this is typically what one of them looks like. It's named a Brownlee particle after the primary investigator, which was Donald Brownlee. So to give you some idea of the size of that particle, you can see there is a bar on the bottom here, and the width of that bar is about 1 micron. So that particle there is probably something like around about 20 to 25 microns in diameter. So that typically is what a cometary particle might look like. We got the opportunity a few years ago to actually study these in more detail when the Stardust probe actually flew past a comet. It flew past Comet Bill 2, and once again it deployed a paddle, and this is the paddle here. It contains these little cells of a material called aerogel, and this aerogel is an easily penetrable material. So as it was flying along and the cometary particles impacted on this paddle, they were trapped in the aerogel, and that paddle was then brought back to Earth and it was analyzed. And one of the principal scientists involved in the analysis of these particles again was Donald Brownlee, and that's Donald Brownlee that you can see there showing the V for victory sign. So you can see that the guys are well kitted up here in their dust-free suits. You can never be too careful. This is what would happen if you weren't too careful. Fortunately, that didn't happen, and so they were able to analyze these particles. So this is a cross-section of the aerogel, and you can see the cometary particles are penetrated, and here's a cometary particle here. There are quite a few in this particular, in fact, there were several thousand of these particles which were brought back to Earth, and they are still in the process of being analyzed. But basically, what the analysis showed is that these solid materials, they contain silicates of the elements iron and magnesium, particularly in the form of the minerals which we know on Earth as olivine, pyroxene, and forsterite. There's also then a form of silica, an amorphous grade of silica with embedded metal sulfides, which we call gems. And then there's a whole complex solid material based on organics of carbon, hydrogen, oxygen, and nitrogen, and they literally call this material CHON. So here is one of these particles which is then looked at under a scanning electron microscope. This is a particle comprised of magnesium silicate, which is the mineral forsterite. And so that typically is a particle, when it comes into our atmosphere, that is what you see as a meteor. Another comet that was a result of a flyby recently was Comet Churyumov-Gerasimenko. That was studied by the Rosetta probe. The Rosetta probe also landed a lander Philae on the surface of this comet. These are particles which were collected in situ by the space probe. They were also analyzed, and they also contain then magnesium and iron silicates, this complex material, and then a number of other things, including sodium, aluminium, and calcium. So this is an image of a comet Churyumov-Gerasimenko taken by the Rosetta probe. It's during its quiescence. You can see that there's nothing taking place on the comet. As the comet gets closer to the sun, it begins to vaporize, and materials start to come off the surface. This again is a picture of the image, or an image of the comet taken from the surface by the Philae lander. So you can see these large cliffs of material, again during quiescence. So as the comet gets closer and closer, it comes under the influence of sunlight radiation, which warms it. It sublimates those three volatiles: water vapor, carbon monoxide, carbon dioxide, and you start to form this coma. And these gases, as they are streaming out into space, are carrying dust particles with them. So we can actually measure the point at which that process of dust formation starts by observing the comet. So these are visual observations of the comet. You can see on the left-hand side you have the absolute magnitude. On the x-axis you have the log of the distance of the comet from the sun. The closest it is to the sun is this point here, the perihelion, which is designated as Q. So the solid points we have here are the comet when it does not show any evidence of a coma. It appears star-like. The open circles are observations of the comet when it is showing a coma. So you can see here that the comet starts to brighten very slowly. As the materials start to vaporize, the brightness of the comet is driven upwards, and we can measure that inflection point there to give you the distance from the sun at which the comet switches on. And when the comet switches on, it starts to eject particles into its path. And that point there, R(on), is at a distance of 6.15 astronomical units from the sun. So in other words, beyond the orbit of Jupiter, when this comet was already starting to emit dust particles from its nucleus. It then passes perihelion, it starts to fade, and conversely we can measure the point at which the comet switches off, and that point at which it switched off was at a distance of 12.56 astronomical units. So the comet is emitting particles from the time it is 6.15 astronomical units from the sun, and continues to emit particles on its outward journey at a distance of 12.56. And if you consider that the furthest point of Halley's comet in its orbit is 35 astronomical units, then it means that this comet is it's emitting particles over quite a substantial arc of its orbit. And considering this comet has been around the sun several thousand times, these particles gradually build up along the orbit and they form the meteor stream as we see today. So this is an actual jet of material which was you can see it was imaged by the Rosetta spacecraft. Just as it was starting to get close to the sun, it's starting to emit these particles into space. There it is side on. And there it is really now becoming quite active. And so when the comet is active and it's actively spewing materials into space, you can see you get these nice dust streamers. This is an image of Comet McNaught 2006 P1, which was very bright in early 2007. It's a picture taken by an amateur, Simon Walsh. We went out to Villiers in the Free State to take this picture. And what you see here is these bands of dust which are given off by the material as the nucleus is rotating in and out of sunlight. So you can imagine if you were passing through, if the Earth were passing through a dust stream left behind by this comet, it would produce quite a nice a meteor shower. So as you were passing through like this, you would see very little. Suddenly, as you hit the stream, you would see an increase in the meteorites. It would decrease and increase, etc. And so over a period of time until you exit the stream, and then the stream disappears altogether. Just to give you some idea, these are particles emitted roughly one day. these are after 2 days, 3 days, and 4 days. So the particles that you're seeing here are around about 4 days earlier. So how many meteor showers then do exist? If you look at the annual meteor showers, these are the showers that are visible pretty much every year to some degree. There is around about a dozen showers. There are 17 meteor showers currently listed in the ASSA handbook, or the Sky Guide Africa South. The IAU on its Meteor Data Center confirmed active list, there are 119 meteor showers. These don't all, they're not all active every year. Some of them are periodic, some of them are random. But on the IAU working list, there is 830 showers. These are showers which have been observed perhaps on one occasion and never again, and they require confirmation. So out of those 830 showers, currently there are only 36 showers who we know what the parent body is, whether it's a comet or an asteroid. So 36 showers. That still leaves us around about 800 potential meteor showers with an unknown parent. And bear in mind that every one of these, because meteors are coming into the atmosphere, they must have been formed by a comet which is on an Earth crossing orbit, and that means that these comets are potentially hazardous, and so it's of interest for us to understand what the parent bodies are, or to give us some idea of where to look for these things if they should come back and pose a hazard to us in the future. So meteor surveillance cameras have been set up worldwide nowadays. They started off with CAMS, the cameras for all sky meteor surveillance. This is an early picture of all of the meteor radiants which were actively detected by CAMS. So you can see here that every one of these dots is a meteor radiant. You can see here that this is the path of the ecliptic, so there are quite a few around the ecliptic. And there are quite a few showers which are active in the northern hemisphere. This is, for example, the radiant of the Perseid meteor shower. And you don't see very much in the southern hemisphere. So why is that? Is it the fact that there are just more showers in the northern hemisphere than there are in the southern hemisphere? Well, the answer is no. This is simply because the early CAMS cameras were all located in the northern hemisphere. There was nothing in the southern hemisphere to detect these meteors, and that's being remedied now. So we have a number of cameras in the southern hemisphere. In fact, the number has grown exponentially in the last 2 or 3 years, and we're now starting to find a lot more meteor showers active in the southern hemisphere that previously were unknown. So this is a snapshot of all the meteor activity in 1 year. We can break that down into more detail and look at the meteor showers which are active in certain periods. So we tend to find in the meteor year, once again, just remember this is the ecliptic. So in early January, the year starts off with the quadrantids. At the same time with the quadrantids, you can see there are a few others active at the same time. So these must be the Comet Halley, the January Leonids, the Alpha Hybrids. So all of these are active during the early parts of January. Further into January, February and March, we can see that there's not a lot going on, but there are a few minor radiants active. Into April, we start to get then the April Lyrids. As we come into early May, we have the most active southern shower for us, which is the Aquariids. During June and early July, once again, it's quite a quiet period. Into late July, we then have a number of showers, the southern Delta Aquariids, the Alpha Capricornids, and the Pisces Australids take place. In early August, we have the start of the Perseids and the Eridanids. Then the Perseids really take over, going towards their maximum around August the 12th. Once again, continuing into September, early September and early October, not too much taking place. In late October, middle of October towards late October, we get the southern Taurids, and then into October the Orionids, which are an annual shower, the maxima of the northern and southern Taurids. Once again, going into December, which is our most active period, we then have, of course, the Geminids taking place over here, a number of other showers active at the same time. So December is our most active period in terms of meteor activity. So all of these have been captured by cameras. The number of cameras is you can see that there's a very high density of meteors, particularly in Western Europe, to some degree in North America. They don't show anything in Japan. Japan seems to have their own systems, and they don't participate in these networks, but they do great work too. There are a lot of cameras in Japan. Not too many in the southern hemisphere at this stage. So these are the cameras that you can see in South America, quite a few. There are a few in Western Australia, Southern Australia, and there's a growing number of cameras in New Zealand. In Africa in general, not a lot taking place in this map. Fortunately, that's now being remedied. So we have a number of cameras which have been installed already in South Africa. The first ones then were the cameras that I've got at my observatory in Bradell. This is the cam setup that I have. There are 8 cameras here, which is this yellow X. And there are another 8 cameras at the Hartbeespoort Radio Astronomy Observatory. And using those 16 cameras, we triangulate meteors and determine their orbits. Shortly after we set up that array, there was an array of 48 cameras set up at the HAC Observatory in Namibia. And that now is the most prolific detector of meteors of any site worldwide, principally because they have very, very good skies, and they have a high number of nights during the year where they have clear skies. And then on the Global Meteor Network, which is the camera that you see at the bottom here, there are a number of cameras now being installed. There are 3 in Bonneville in the Western Cape. Lo Ferreira in Quebec, he has 2 cameras, and Paul Ludick up here in Hartbeespoort, he also has 2 cameras. So this is the GMN camera inside a standard security camera mounting, and anybody can buy one of these cameras. You only need 1 camera to participate in this program, and set one up, and you can also participate in these detections. So this is typically the output from my cameras. These are a number of captures. This is a Capricornid, a South Delta Aquariid, Capricornid, etc. This was a sporadic meteor. So this is how these appear. You can see that in these images, we also have a number of stars. So the software does the calibration of these images. It measures the astrometry of the start and endpoints of the meteor using these stars as references. Also measures the brightness of these objects. And then by triangulating with another station, we can determine the orbits of these objects. So that is the typical field of view of a CAMS camera. And then this is a stack of images throughout one night from one camera. This is Paul Ludick's camera number 4 in Hartbeespoort, and you can see this is a picture that he took, or this is a stack of the images he took of principally the Eta Aquariids taken during the nights of May 9th and 10th. So most of what you see here are meteors. There are 1 or 2 things here. This is a satellite that you can see flashing as it goes along, but most of these are meteors. And so if you set up the camera and you have it overlapping with Paul's cameras, we can determine the orbits of these objects as well. So these cameras are now picking up new showers. This is a picture of Comet Finlay. Comet Finlay was discovered by William Finlay in 1886. from the Cape Observatory using the 7-inch refractor there. It's a comet which is, it returns to the Earth every 6.5 years or so. It's a periodic comet called 15P Finlay, so you can still see this comet. And despite the fact that the orbit of this comet comes quite close to the Earth's orbit, a meteor shower was never seen from this particular comet. In 2014, this comet underwent a very bright outburst by several magnitudes, up to around about magnitude 5. It's very rare that happens, but it was visible with binoculars for quite some time. And based on that outburst of 2014, astronomers modeling the orbits of the particles coming from this comet predicted that a meteor shower should be seen in 2021 during the month of September, and our cameras duly did pick that up. We found that the meteors from this particular shower were visible coming from the constellation of Ara, and so this meteor shower, which is now associated with Comet Finlay, is referred to as the Aquariids. So that's what you can do with a camera. ASSA has also done some very, very good work on visual observation of meteor showers, particularly the Eta Aquariids. The Eta Aquariids are one of two showers which are spawned by comets Halley. This is a picture of Comet Halley back in 1986, which was taken by the Giotto probe. So you can see these jets here active, and these are carrying materials into space in the orbit of the comet. So this is the orbit of Comet Halley. It was at perihelion in 1986 in its 76-year orbit. It then goes back out into space. This is the position in 2024 when it's at its farthest. It then comes back into the solar system, and it will be at perihelion again in 2061. So it's done this several thousand times in its 76-year orbit. It was first observations of the shower from Halley's comet were in around about the year minus 1440, so 1440 BC. It's been rotating around the sun pretty much since then, every time, and that meteor stream then is gradually building up, and it forms now a complete loop around the orbit of Comet Halley. So in its orbit around the sun, we cross the orbit twice. It's actually quite rare that we get meteor showers two from the same comet, but we do so with the meteors from Comet Halley. So the first occasion here is when we cross the stream in October on its inward path, and that gives us the meteor shower which we know as the Hermanus. The meteors continue to go around the sun past their perihelion, and then on the way out here at their descending node, we get what's called the Eta Aquariids, and that happens each year during May. So in the first week of May, we have the Eta Aquariids meteor shower. Duration roughly from around about 15th of April is the first that we start to encounter the stream. It continues until around about the 28th of May. The maximum normally takes place around about the 5th or the 6th of May. And the zenithal hourly rate, which is the number of meteors that we would expect to see if the meteor shower was at the zenith, and you were under dark skies with stars around about magnitude 6.5 visible, would give you then a rate of around about 60 meteors per hour. On occasions, there are outbursts to about double that, so around about 120 kilometers per hour. So the speed of these meteors is very fast. They're easy to spot because of their speed, about 66 kilometers per second that they're entering the atmosphere, and they are visible on early May mornings between 3:30 and dawn. So this is what an Eta Aquariid looks like. If you know your constellations, if you know Aquarius, there are 4 stars here, which is the water jar asterism. The Europeans like to refer to this as the Mercedes-Benz logo, but it's the water jar asterism, 4 stars, and you can see that this meteor, if you track it back, it comes back to this point here, which is here at Eta Aquarium. So if you want to participate in this, you can do so quite easily. You don't need any equipment at all. It's just a case of laying back on a reclining chair and counting the number of meteors that you see coming from this particular radiant. And that can give us some good information. So the most simple thing, of course, would be to just count the number of Eta Aquariids and divide that by the amount of time. If you spend 1 hour and you see 15 meteors in that 1 hour, then the rate is 15 per hour. But that particular equation does not give you any indications of the conditions of the skies that you observe under. And also, it does not give you any indication of how high the altitude of the radiant was above the horizon. So there are a couple of other things that we can do. We then, what we do is we determine the zenithal hourly rate. And as I've said, the zenithal hourly rate is the number of meteors that you would see if the radiant was at the zenith, and if you could see stars to the limiting magnitude of magnitude 6.5. So under conditions different to that, we need to make a correction. And we do so then by correcting for the limiting magnitude, and we do so by correcting for the time. So we need the actual time in universal time that you made the observations, and from that we can work out from the sign of the altitude, we can work out the correction factor for the altitude. Okay, so if we have all that information, and once again, as I say, you can do that with nothing more than the naked eye, and just some diligence and making those particular measurements. Given that you measure the zenithal hourly rates, we can then plot the zenithal hourly rate against the date, or in this case, the solar longitude, the longitude of the sun, which then takes away the vagaries of having a leap year every 4 years. So that gives the sun's position, the Earth relative to the sun. This is the zenithal hourly rate, and you can see here then from 1997, for example, that the rate in early May starts to increase slowly. It reaches a peak here at around about the 5th or the 6th of May, and then after that it starts to decrease. It's not a regular increase and a regular decrease. You can see that there are ups and downs, and the reason for that is because we pass through these different streams of particles which were left behind from the comet as it was rotating in and out of sunlight. So remember then that the zenithal hourly rate here, typically around about 60 per hour. That was in 1997. If we look at the picture, for example, in 2012, this is the rate profile based on global observations for 2012. Again, somewhere around about 60 to 70 per Eta Aquariids per hour. But clearly in 2013, it was different. And in 2013, there was an outburst. And you can see here that the zenithal hourly rate, it's around about 120 to 125 at its maximum. So those periods when we have these outbursts, they seem to come around about every 10 or 12 years. The possibility is that there is a relationship between these outbursts and the orbit of Jupiter, because Jupiter also goes around the sun in around about 12 years. So every 12 years it encounters the stream and it perturbs it and gives us, it enhances these rates. So this is the rates from the Eta Aquariids right the way back from 1985 up to 2020. And you can see that there's an outburst here in 2004. There's another outburst here in 2013, which I've already showed you. And based on modeling from these observations, astronomers determined that there should be another outburst either in 2023, that's this year, or 2024. So we've just come out of the this year's apparition for the Eta Aquariids. Myself and Master Striker, we conducted some good observations on this shower before the weather intervened, and we managed to observe right away from the 2nd of May up until the, you can see here, the 7th of May. The peak normally peaks at around about the 5th and 6th of May. We found this year that the peak was 1 day earlier than previous, and also, surprisingly, it's a very, very low activity. So despite the fact that there was a full moon for these observations, the rates nevertheless of the shower were far below what we expected. So we are hopeful that 2024 will be the year when there will be an outburst from the HAC Aquariids. So these observations were made using nothing more than the naked eye and a pencil and a notepad, and just recording the number of meteors that we saw, doing the necessary calibrations, and then it gives us some very good data on these meteor streams. You can do it yourself. You can participate in this program, whether you have a dark sky or you have a very light sky. You can still do useful work. So just to give you some example, this is the sky pollution map for Gauteng. You can see here that these areas are quite dark skies. As we go into the green, the light pollution increases. Yellow is much worse. Orange, and then eventually these red or pinky areas. These are areas of very high light pollution. And the location of that target there is my site in Bradell. I do meteor observations from here, from a relatively light polluted site. Not only visual observations, but also then with the 18 cameras that I have, 16 cameras that I have. And so we've done some very, very useful work, even from light polluted skies. So that's my situation. I think I'm right in saying that that is your situation. I think the people that I'm talking to tonight, most of you are here. And so your skies are infinitely better than mine. And so with that, I would like to invite you, if you're interested, to get in contact and make a contribution to the observation of meteors. Thank you very much.
Is that it, Tom?
That's my presentation. Thank you.
Thank you very much. That was fascinating. Great detail there. Quite a few images of protostars and stuff that I don't think I've seen before. I've got a question before we go to the questions of the group. And about a third of the way in, where you had all that detail, I think from Comet Halley, all the chemical analysis and so on. It was quite fascinating. Yes. I never realized there was that huge amount of variety. But you had there was one nitrogen, and there was sort of a cryptic description there of including biologically active compounds. What exactly does that mean?
Amino acids.
Yeah, so it is, if those, in other words, what it means is if those chemicals were on Earth, then they could be involved in biological processes on Earth. It doesn't mean that yes, there were biological processes happening on that comet. In other words,
no, and it's very unlikely that biological processes
would be rather exciting if
where they came from.
Okay, any questions from the attendees? Tim?
Peter Kotze here. Tim, thank you very much for a very fascinating presentation. I just have one curiosity, and that is it possible to determine the amount of mass that comes of all these meteors during a meteor shower? Have you got any calibration or method to determine the amount of tons or kilograms that comes into the Earth's atmosphere during a particular meteor shower?
Yes, so I don't have that figure off the top of my head, but based on the meteor rates that we determine visually, I showed you those rate profiles. Those rate profiles are then converted to a meteor density in the number of particles per square kilometer. So if you can make an assumption in terms of what the average size of those particles is, and because you know what that meteor density is per square kilometer, it's possible to calculate what the amount of material coming from a shower per day. So that could be done. I don't have the figure off the top of my head, but it could be determined. But the amount of material that comes into the atmosphere every year is somewhat controversial. It depends on who you speak to, but it varies anything from 2 tons to 200 tons per day.
Thank you very much. I appreciate it.
Great stuff. Anybody else?
Tim Pierre de Villiers probably had a very dumb question. I was also surprised at the complexity of some of the compounds found in the analysis of meteors. Now, obviously, all the meteors that we observe now and whose dust we analyze were formed from the same giant molecular cloud as the sun, the solar system. Is there any relationship between the complexity of the molecules found in comets to the number of recycling, let's call it supernova recyclings? Because the material in our current solar system came from one, let's call it one supernova explosion, but there could have been previous generations. Is that speculation, or is there some logic behind it?
No, it's absolutely correct. So, all of these stars go through the process of converting hydrogen to helium, helium to carbon, carbon to oxygen, oxygen to silicon, silicon to iron, etc. And then, so all of those those elements are during the lifetime of the star. And then all of the other elements are generated during these supernova explosions. So, I mean, these giant molecular clouds, they're vast areas, and they contain a lot of material and a lot of old stars, which have gone through at least maybe 2 or even 3 lifetimes. These giant molecular clouds, they become quite complex. And then once these materials have been ejected into these giant molecular clouds, depending on how close these materials are to very energetic stars. These very energetic young stars, they have very active solar winds, high energy radiation, and they synthesize these molecules even further. So you start off with these what we call the daughter parent compounds, and then you've got the daughter molecules, which are built up from these materials, which are in these giant molecular clouds, and they come under the influence of these highly energetic stars. So, and that composition varies within a giant molecular cloud, depending on how close these materials are to these energetic stars. The composition of these clouds is not uniform; it's heterogeneous.
Thanks. That's a very complete answer, Tim.
Right. Let's see who our participants are. All right, I'm sure there must be plenty of questions, comments. Anybody?
Can I say something?
Go ahead, Magda.
Magda Stryger, can I say something?
Go ahead, Magda.
I just want to say that we are so privileged in South Africa to have such a good man like Tim Cooper. He is such on top of his game, and for so many years. And to me, it's a privilege to now and then observe with Tim and really He is so valuable for us, and the work he done in the world and for South Africa is immense. Thank you.
Thank you, Martha.
Well, it was certainly a very impressive talk, and anytime I learned such an enormous amount, which I never knew before, I find it very refreshing and very pleasing, very valuable experience. Thank you.
Pleasure.
I see Paul Ludick is also attending. Exactly where do you observe in Hartbeespoort, Paul?
Non-Pier, yes, I'm here on the what they call the working class side of the dam, the eastern shores. It's where the mall is in that. It's not on the western side where Peakenwood and those places are. So it's on the northeastern shores of the dam, between Schoemansville and Ifafi.
It's also quite light blue today.
Indeed, if I recall correctly, I think we've got a bore till 5. I might be under correction, but yeah, it depends. If it's a Friday evening or worse, a Saturday evening, it's all the brass that's going here around the dam. But otherwise, we've got pretty good seeing. I must say, we're not that bad out here.
Thanks.
We're counting Bryce Sparks and Elon Musk satellites.
Yep, indeed.
Paul is doing some great work. He has 2 cameras as part of the GMN, and we are busy bringing in some more cameras at the moment, and I'm hoping very soon to be able to put a couple of cameras up and triangulate with Paul so that we can do orbit determination of meteors using his cameras.
No, indeed. Just to add on that, Tim, when we set up the cameras, we had a real logistical discussion between Dennis Vida and Michael Mazer, the chap in Canada itself that I dealt with, and they asked me which direction do we want to point, and I said, well, what's the scientific preference? So they said, look, it's not really a big issue. So I said, look, if I have to be materialistic, I want to point to a place that if there is what's referred to as a dropper, that it's actually a safe location to go to. We don't want to end up into difficult, harsh environments, where your car's going to go missing or the likes. So from my location, we agreed that we'll pretty much go into a south-southwest to a west direction on the one cam, and then the other one would overlap towards a northerly direction. So obviously with the ultimate, I'm not saying that it's the Eureka, but you've been fortunate to go and hunt and pick up a dropper in bots, if I recall. So that's why we set it up that way. However, as time goes along, we'll definitely add 2 more to try and get a further coverage on the other areas we've not yet done.
Yeah.
Okay, can I ask a question? The practicality of triangulating, what exactly does that? How does that work? I mean, do you work out sort of what your angle of your camera was and identify that another camera had the same meteor at a different whatever angle? And I mean, how do you
Yes.
identify that one image is in one camera is the same as the other one in the other image? And
Yeah. So to do triangulation, you need cameras at 2 different sites, which are separated around about 100 to 150 k's apart. And then, so if you take my cameras at Bredell, then I've got, which is Kempton Park, and then on the other side of Gauteng, actually quite close to where Paul is at Hartbeespoort Radio Astronomy Observatory, I've got another 8 cameras. Now those cameras are aligned so that they overlap each other. So my cameras are pointed at a point 95 kilometers above the Earth's surface, and the cameras in Hartbeespoort are are aligned that they look at the same spot, but from a different perspective. So any meteor coming through that spot will be picked up with my cameras and the HAC cameras, and then they're connected to a computer. The computers have to be synchronized to better than less than a second. So the cameras will capture those meteors, and based on the fact that those meteors came in at the same time, everything gets uploaded then to the server. It does the calibrations of the start and end points of the meteor train using the background stars. So we know the right ascension, declination, etc. of the path from both sides. And then once you've got that, and because you know the positions of the cameras accurately, and you know the time accurately, then given all of that, the computer that does the number crunching that comes up with the orbit.
Interesting. Okay.
Tim, I've probably reached the incorrect conclusion, but I got the idea that cloud cover or lack of cloud cover is probably more important than the light pollution, because I mean, you and Paul are definitely in fairly light polluted areas. You also showed that there were some cameras in Port Elizabeth or Canberra. Now, anywhere where you're close to the sea, you are subject to more cloud cover than you would be inland. How successful are the cameras at Canberra? Because I think this might be something that we could be interested, maybe in conjunction with schools, Derek. I think we should at least discuss the possibility.
Sorry, Pierre, I just go ahead.
Yeah. So yes, I mean, if there's clouds, obviously, then you know you can't spot meteors. So it's just that simple. We found that light pollution is not a big effect on the data. The cameras that I have, they even in the environment that I'm in, which is a relatively light polluted area, and I'm quite close to, for example, OR Tambo International Airport, which is about 7 kilometers from me, and the light pollution in that direction is horrendous. But so despite that, my cameras can pick up magnitude 5 meteors. So you know, our output is not really limited by light pollution. But if there's cloud, then yes, you know, obviously the cameras can't be functional. I haven't seen the data between Lowe's cameras and Paul's cameras, for example. They have the same cameras. I don't know how many nights Paul gets compared to Lowe down at the coast. I guess there must be a difference, but I'm not sure what that is. But I would not let that discourage you. If you want to put cameras down your way, then we should do so. And as I say, we've got 4 cameras coming in at the moment. We will probably keep 2 for up here, and we could certainly spare 2 to come down your way if you wanted to. The stipulation for these cameras is that they have to be used by school children. So if you want to do a project together with schools, then we're very much open to looking at that potential.
Thanks for that.
We'll definitely discuss that at our next committee meeting.
Excellent.
Great. All right, that's been quite a comprehensive talk. If there are no more questions, then we'll wrap it up. I'll upload the recording to YouTube, and I'll send you a link tomorrow or so.
Thanks a lot, Tim. That was excellent.
My pleasure.
All right, thanks everybody for attending, and thanks for a fascinating talk, Tim. It was really worthwhile.
Thanks for the invitation. I appreciate it.
Great. Okay. Okay, everybody, I'm going to end the recording now. No other questions before we shut off? None? Okay. End the recording and end the session. Thanks very much. It's great stuff.